Hello everyone. So today I will be presenting on alpha magnetic spectrometer in this video, which is a particle physics experiment that has significantly advanced our understanding of cosmic phenomena. I am Mandar Khalke, and this presentation we will explore alpha magnetic spectrometer's basic design, functionality, and its some contribution to the science. So next slide. Alpha. What is alpha magnetic spectrometer? It is a high-energy particle detector which is mounted on International Space Station in 2011 in the month of May from Kennedy Space Center. It functions as an high-energy particles. It studies the cosmic rays, which are high-energy particles originating from outer space. By analyzing these particles, AMS addresses fundamental questions about the universe, such as its origin, composition, and structure. It also investigates dark matter, antimatter, key elements that remain mysterious yet are integral part of our cosmos. So we can see the diagram of AMS. It consists of uh, six detectors, a magnet, and different types of detectors which are arranged sequentially. So why there is need of AMS? So we'll see why there is what is the need of AMS. So when it comes to understanding our universe, we are only at the beginning. So we are continuously evolved, and the searches for the pattern in the universe is tells us how the universe work. How does a solar system, planet, galaxy fit in with the other pieces of the universe, and what are we not knowing yet? Helping us discover more pieces of this puzzle will be our this new instrument called as alpha magnetic spectrometer. It is not a telescope. Rather than looking in the space, it will sift through the space by studying high energy particles such as cosmic rays from a unique vantage point, which is the Earth orbit. It cannot be operated from the Earth as cosmic rays interact with the Earth's atmosphere, and the energy with which they enter the Earth's atmosphere after entering it becomes zero, so that it does not reach our Earth's surface. The air and the protective ozone layer and all the atmospheric content in the upper at the stratosphere, troposphere will will finish the energy of the cosmic rays. So we can't keep alpha magnetic spectrometer on the Earth. So it all the start of universe at the start of universe there was a big bang as uh, as Big Bang theory. We call it as Big Bang theory, which postulate that universe was created with a great explosion. But there are many pieces of puzzle missing. During this explosion, many types of matter and antimatter should have been created in equal amounts. But we are not finding antimatter. So by studying cosmic rays, we can find these traces of antimatter, potentially shedding light on the why the universe is mostly matter. Also, the dark matter detection. The AMS seeks evidence of dark matter by detecting high energy particles, as traditional telescope cannot see dark matter directly. Also to study the cosmic ray composition. So what is actually cosmic ray made up of? And cosmic rays come from a large distance, and mostly contains charged and high energy particles. So what are those particles? We need to study. So AMS operates at International Space Station, where it can easily take cosmic rays and detect it with the help of different types of detectors, which we'll see further. So why there is need to study antimatter and dark matter? What is dark matter? So dark matter is the mysterious form of matter that does not emit any light or energy. Hence, it is called as dark. Scientists estimates that most 27% of our universe is made up of dark matter. With dark matter, it does not emit light or absorb light, but it has gravitational effects, which is essential to formation of the structure of the galaxies. And now we'll see what is antimatter. So antimatter is composed of particles which are mirror opposite that of regular matter. So for example, we can see one of the antimatter is positrons, which is just like electron but having positive charge. So antimatters are the particles that annihilate matter upon contact, releasing vast amount of energy. So these energies are detected by our alpha magnetic spectrometer. The universe today has far more than antimatter, which AMS tries to investigate. So importance of studying this dark matter and antimatter by by studying the components, it is crucial because they could unlock a fundamental insights into universe. Dark matter affects galaxy formation as it has gravitational effects on other planets and solar systems. So both help physicists refine the theories and models of the cosmos, potentially leading to groundbreaking discoveries. So working principle. So AMS works of detecting of cosmic rays by a system of detectors. There are different types of detectors uh, which which are placed on AMS. The detector measures the properties such as charge, energy, and the velocity of the cosmic ray particle. So there is a magnet in the core of the AMS which uses due to its magnetic field, which is more than 3 to 400 times more than our Earth's magnetic field. It bends the particles which pass through different types of detectors, which measures the charge, the energy, and the speed of the cosmic ray particles. This data is collected, which helps to differentiate between particles, which include rare antimatter particles, high energy cosmic particles, and also the particles which could be from the dark matter, which could be from the dark matter, means when the dark matter interacts with some matter, it releases energy, and the energy is detected by these detectors of the cosmic ray, and we can also find the origin from where the rays have emerged and came to our detector. So this is the path of the cosmic rays. V is the V for time of flight, Q is the magnitude of energy loss, and Q sign from direction of the curve. So this is time of flight. There are many detectors placed, and a magnet curves these particles. So we'll see next components of AMS. So there are key detectors which include STD, which is silicon detector tracker, then TF, time of flight detector, TRD, transition radiation detector, RICH, which is which is imaging Cherenkov detector, and ECAL, which is electromagnetic calorimeter, which remain unchanged despite of magnetic switch. These are placed between the magnet. The rigidity range is from 0.5 giga electron volt for tera electron volt. So the measuring of cosmic rays is from this energy range. So high energy cosmic rays can be also measured. And magnet configuration, it was originally a superconducting magnet, but now ASM02 is swapped with a permanent magnet. So there is permanent magnet installed. This is the diagram. We can see the AMS showcasing key detector and its components. This includes main are silicon tracker detectors involved here. The magnet is there. Then there is the helium vessel, which is used for cryogenic magnet. Then there is a time of flight detectors, S1, S2, S3, S4. Then there is cryo cooler to maintain the cooling system. Then there is star tracker, then TRD, which is transition radiation detector. RICH is here. ECL is electron calorimeter, and a vacuum case, which helps the magnet to maintain its low temperature. Next, here is also one of the detailed views. The time of flights, scintillators. Scintillators are here. There are photo multipliers on time of flight detectors, which what we can say, photo multipliers means it multiplies the amount of it maximum multiplies the amplitude. So there are photomultipliers in each of the detector, which multipliers supplies the amplitude of the detection. So this is the open view. So now we will move to each and every part of the what we can what is this? AMS, alpha magnetic spectrometer. So cryogenic superconducting magnet. So superconducting magnets bends the charge of the particles of multi tera electronic tera electronic volt measurements. So high energy particles are bent using this magnet, which is so it includes the detectors include silicon tracker TOF. We have seen this earlier. So say magnet design minimizes stray fields for NASA safety and complication compliance on ISS. So the magnet only produces the fields which are involved, which do not harm ISS, which do not harm, we can say, International Space Station. These magnetic fields are only valid in the instrument. They do not come out of the instrument. So cooling it operates at 1.8 Kelvin. We can see it is a very low temperature, and hence cryogenic superconducting magnet, we can say, was installed, and it is used, and how this helium vessel which contains helium cools the magnet and maintains the 1.8 Kelvin temperature. So silicon tracker detector, which is made up of 8 double-sided silicon layers. 6 of them are contained inside the magnet, which will measure the charged particle bending. So it is the core of AMS, which measures the particle momentum in a strong magnetic field. We can see the trajectory of the particles coming through the detectors. There are 2,300 silicon microchip sensors in 8 circular layers. There are 8 layers of 6.5 meter square surface area and about 1,96,000 readout channels. Resolution, it achieves 8.5 micrometer bending plane and 30 micrometer non-bending plane precision. The stability, the laser alignment of the system maintains 4 micrometer accuracy. The rigidity and charge detection, it measures rigidity up to 1 tera electron volt and separates the nuclei up to Z equals to 26. So time of flight detector, light production, it produces light. The light is produced and flashes when the photons hit the detector. It is used for velocity measurement and provides fast trigger. 4 planes of ski- scintillator viewed by photomultiplied flare tubes. Its direction, it detects the direction, and downward particles which travels with 120 picosecond resolution. Pico 10 raised to minus 13 second resolution. It's so fast. So structure consists of 4 siliconator planes that measure particle transit time between 2 layers. So time of flight between 2 layers, how much time taken by the particle is measured between this. That is the velocity is measured. So anti-coincides current, we can see the figure of the instrument. The upper figure shows ACC of after integration. This is after integration. Right side image shows the component, and the lower shows ACC working principle. WLS fibers are installed. The charged particle passes through these WLS fibers. It identifies particle entering from side and not cleanly passing through silicon. That is, this uh, ACC identifies that particle that do not pass through center of silicon detectors. That is, the particles which are missed from silicon tracker is identified by ACC. It helps reject the particle that could interfere with accurate charge measurements. It also acts as veto for time of flight triggered events from side particles or secondary interaction. Consists of 16 scalar panels in a cylindrical layout with UV captured embedded WLS fibers. Its specifications has low inefficiency, less than 10 raised to minus 4, and a power consumption of 800 microwatt, which my 800 milliwatt, sorry, milliwatt, and weighs up to 54 kg. Now this is RICH detector, ring imaging Cherenkov detector. It is used for velocity measurements of the charged particle via Cherenkov light cone angle. This cone angle, there are many photomultipliers and light guides. The sodium fluoride and aerogel is used for light emissions. Light is produced when the charged particles pass through it, and measuring the light and measuring the velocity is done using that. It uses photomultiplier to measure Cherenkov light. Cherenkov light passes through this detector on the photomultipliers, and the time required is captured, and then the velocity is measured. ECL is electromagnetic calorimeter. Uh, Particle ID and energy identifies electromagnetic particles measuring electron and gamma energy up to 1 tera electron volt with 3% resolution at 100 giga electron volt. Structure: it consists of 9 lead and silicanating scintillating fibers modules forming 3D imaging calorimeter. So there are two electronic gains. There is magnetic shielding of about 200 Gauss residual field. The energy range it measures is from 1 giga electron volts to few teravolts, that is high energy. And efficiency is greater than 90% of gamma detection of above high energy particles of energy greater than 2 giga electron volts. Now TRD, which is transition radiation detector. The purpose, it detects the transition radiation emitted by particles such as electrons and protons. Positrons are the anti-counter, that's counterpart of electron, which is an antimatter. So distinguish between from the other heavier particles. It only detects electrons and positrons. So it reduces proton background, achieving overall rejection 10 raised to minus 6 and at efficiency 90%, which when used with ECL, that is electromagnetic calorimeter. Its structure contains 20 layers of trough eye tubes and fleece radiators arranged in octagonal structure. The gas mixture is of 80% xenon and 20% CO2. The 3D tracking provides particle tracking and identification in both magnetic field directions. So it is a hexagonal structure you can see from it, or octagonal structure you can see from it. Next one is AMS multipurpose spectrometer. Now this is the in depth view of the our instrument. So TRD identifies electrons and positrons, which is at the upper side. Then at second, we can see time of flight detector, which measures the Z charge and E energy. And then third is the magnet. Then there are silicon tracker detectors we can see, which are placed in between all the detectors, which measures the charge and the momentum and the charge of the particles. Then we can see the magnet, which bends the path of the cosmic rays so as they pass through all the detectors uniformly. And the electromagnetic calorimeter at the last, you can see it measures the energy of electrons. The ring imaging Cherenkov, which is placed above electromagnetic calorimeter, which measures the charge and energy. Also, it RICH, we have seen it measures the velocity using the Cherenkov light. Its top layer was sodium fluoride and aerogel, which produces light, Cherenkov light when the high cosmic rays particle pass through it. So this is how charge, energy, and momentum are measured independently by all these detectors. Now detecting antimatter. So key detection of antimatter is detecting positron, which are the counterpart of electron. So AMS 02 looks for an excess positrons and antiprotons in the cosmic ray spectrum. This would suggest that particles might come from dark matter interaction or other exotic sources. That is cosmic ray spectrum. It looks for excess of positron and antiproton. So when these positrons interact with electrons, they annihilate each other, releasing energy. So these specific energy signatures are detected by AMS02 that measures the energy spectrum of the particle and looks of excess positrons or higher energy and other signal of antimatter interaction. It detects an anomaly in the ratio of positrons to electrons. This signal could be that dark matter is decaying or annihilating into standard particles, including positrons. So the cosmic rays from where they are coming, that is any part of universe, would contain this antimatter, and that is due to decaying of dark matter. So detection of dark matter. Dark matter is theorized to consist of unknown particles that do not interact with light. Hence they are called as dark matter, but have but have mass and gravitational effects. So they are also known as weakly interacting massive particles or exotic particles. The AMS searches for indirect signals of dark matter, such as unusual excess high energy particles that could result in decaying or annihilation of dark matter. One of primary signature of AMS02 is excess of positrons and antiproton in cosmic rays. If dark matter particles such as weakly interacting massive particles, they could be decaying or annihilating into standard particles like positrons, which produce excess uh, amount of positrons, and that AMS could detect using energy spectrum. Anomalies in the spectrum, particularly at certain energies, might indicate presence of dark matter decay. So dark matter can can have energy up to 1 tera electron volt, and that can be detected by AMS. And collision of cosmic rays with IMS is shown in this diagram. So in summary, AMS not an it is not an telescope. A telescope measures photon packages of light, both visible and invisible to naked eye. But this type of astronomy has given us most of the knowledge as far. But cosmos speaks in to us at language other than light. The AMS. This will be first time that the scientists study charged particles of exploding stars and other celestial phenomena, and are thought to produce cosmic rays which travel across the universe and wash up to shores of planet. Rays are completely composed of charged particles, but many of these are absorbed in our atmosphere by making them difficult to study on Earth. So our atmosphere does not cannot contain this AMS. So we need to take it to International Space Station so that AMS will be able to shift at the particles, helping us search for antimatter and dark matter and the other stuff which universe is hiding from us. So particles will pass through AMS layer upon layer detector that will tell the mass and energy and velocity of particle. Other detectors will tell in which direction or path uh, took as it passed through the detector. And the heart of the unit, there is a magnet that will make the particles to curve and pass through the detectors, telling whether it's antimatter or dark matter. So the data is collected very fast. There are 25,000 hits per second of cosmic rays. Also, there are 3 lakh data channels for detection and 600 onboard processors to analyze the data. So we can conclude from this that AMS does not directly detect dark matter, but its observation can provide us indirect evidence of how what is dark matter present existence in the its cosmos in this cosmos, and the data can also give presence of dark matter and antimatter. So from this I conclude the session. Thank you. Okay, bye.